Okay, now we're going to look at the derivative of y equals e to the x. So this is an exponential function with a very specific base. So instead of talking in general, base b, we're giving it a very specific number. It's important to look at e like pi. Pi is not a variable, it's a number. We use the symbol to represent the number because it's non-ending, non-repeating decimal. Well, Euler's number is the same. I know this looks like Euler, but it's actually pronounced Euler. They use E because it is the first letter of his name, and it's 2.718281, and again, this goes on forever with no pattern. So often it's rounded, but that's why if you look on your calculator, you should have an E button on there. So if you're ever calculating something that has a base E, instead of going 2.7 or 2.718 to that exponent, you would use your E button. So the function we're going to work with is f at x equal e to the x. And I'm going to repeat the process that we did for b to the x in the activity. So I'm going to use my limit definition for the derivative. So the derivative is the limit as h approaches 0, f at x plus h minus f at x all over h. Now my function, f in this case, is e to the x. So I have e to the x plus h minus e to the x. I use my laws of exponents to take e to the x plus h and write it as e to the x times e to the h. Now I can common factor out an e to the x, and I get the limit as h approaches 0, e to the x times e to the h minus 1 all over h. Because the e to the x has no h involved in it, it can come in front of the limit notation. So I have e to the x times the limit as h approaches 0, e to the h minus 1 over h. And remember, in the activity, we talked about this. This represents f prime at 0, or the slope of the tangent to e to the x at x equals 0. And the whole discovery of e was based on that is going to equal 1, because e is the base where if you drew the tangent at x equal to 0, the slope of that tangent would be 1. So all of this here goes to 1. So e to the x times 1 is just e to the x. So it's pretty cool that in general, if f at x equals e to the x, then the derivative is e to the x. So it is a function that the derivative is equal to itself. But now we're going to look at, well, what if the exponent isn't just x? So the exponent has something going on. So the exponent itself is another function. I'm going to call it g. So an example might be x squared or 3x. So if you have f at x equal e to the g at x, the derivative, and we're going to use chain rule. So the outside derivative is the e. So then the derivative of e is still e. So the derivative of e is e. I keep the inside the same because I'm thinking of my exponent as the inside function. But then chain rule says I have to take the derivative of that function, which would be g prime, and multiply it. So hopefully will make some more sense as I do some examples. So example 1, we're going to find the derivative of f at x equal to x squared e to the x. So this is product rule. This one is a power function. This one is an exponential function. The difference being that in this case, I don't know the base, but I know the exponent. In this case, I know the base, but I don't know the exponent. So the derivative is going to be the derivative of the first. Well, the derivative of x squared is 2x times the second plus the first times the derivative of the second. And this is where it's going to look a little weird because it's going to look like I haven't done anything to e to the x, but the derivative of e to the x is e to the x. Now, because e to the x is its own derivative, when you start doing rules like product rule and quotient rule, you're going to see e to the x pop up a lot, and I want you to get used to common factoring. If I look at this, both terms have an x, and both terms have an e to the x. So then I'm going to have 2 plus x in the bracket. This is just a way of simplifying it, but as we do further examples where we have to work with this and solve it, this is much better. Example number 2. G at x equals e to the x squared minus x. So this is just an exponential function. X squared minus x is all in the exponent. So g prime at x is e to the derivative of e is e to the. And I don't say a lot after the because it's whatever the exponent is. So the derivative is e to the x squared minus x. But because the exponent itself is a function, chain rule says I now have to look inside at this function and multiply by its derivative. Well, the derivative of x squared is 2x, and the derivative of negative x is negative 1. And make sure it's really obvious that this part is an exponent and this part is not. It's a multiplication at the end. Okay, find the value of f prime at negative 1 for f at x equal to 3 to the e x squared. Sorry, 3 times e to the x squared. This is another way of saying what's the slope of the tangent at x equal to negative 1. So if f at x equals 3e to the x squared, this isn't product rule. This is a constant multiple. There's no variable in this 3. So to do my derivative, it's just 3 times the derivative of this. So the derivative of e to the x squared, I start with e to the x squared. But because my exponent has something going with it, I have to go back and say the derivative of x squared is 2x. I can multiply those two pieces together. So my final derivative is 6xe to the x squared. So now I can sub in negative 1. So that gives me 6 times negative 1, e to the negative 1 squared. So that's going to give me negative 6e. 6 times negative 1 is negative 6. And negative 1 squared is positive 1. E to the positive 1 is e. This is a number. If you wanted to get the number, you could go negative 6 times e using the e button on your calculator, and that would give you a more tangible or a number representation of the slope of the tangent. But there's nothing wrong with having negative 6e as a slope. It's the same as having like 2 pi as your radius when you're talking about circles. And one more example where we actually find the whole equation of a tangent with an e to the function. So find the equation of the tangent to y equals x e to the x at x equals 2. So again, whenever they want an equation of a tangent, I'm looking at modified slope. My point, I have my x, so the bottom is going to be x minus 2. To get my y, I'm going to take 2 and sub it into here. So at 2, y equals 2e squared. I'm not going to go and ask my calculator what that is as a decimal. I'm going to leave it as 2e squared. And I put it in for my y. Now to find my m, that is the derivative at x equal to 2. So I'm going to go back to this original function and I'm going to start finding my dy dx. And again, I'm going to use product rule because there is a variable in this first part. So the derivative of the first, x, is 1 times the second plus the first, which is x, times the derivative of the second. Well, the derivative of e to the x is just e to the x. And because my exponent is 1, my exponent is x, the derivative is 1, so I don't have to multiply by it. I'm going to common factor out an e to the x, and I get 1 plus x. And now I'm going to put 2 in for x. So that's going to give me e squared times 1 plus 2, which I'm going to write as 3e squared. Again, I'm not going to change that to a decimal. I'm going to work with that as my slope. So my slope is 3e squared, which I can think about as 3e squared over 1. I'm going to cross multiply. So 1 times y is y. 1 times 2e squared is 2e squared. 3e squared times x is 3e squared x. 3e squared times negative 2 is negative 6e squared. And now I'm going to bring everything to one side and set it equal to 0. Because my x term has to lead and has to be positive, and it's already positive on this side, I'm going to leave it on that side. I'm going to bring the y over, so it's going to become a minus y. And I have negative 6e squared, but when I bring this subtract 2e squared over, I'm going to end up adding it, so it'll be negative 4e squared. So this is an equation of a line. 3e squared is a number. If I use the e button, I'm getting a decimal approximation for it. If I leave it as 3e squared, that's an exact number. And same with minus 4e squared, that's a number. That'll be my constant at the end. So I do get a standard form equation of a line. It just looks a little different than what we're used to.